In this video, we will be covering Chapter 7, Section 3 of the AP Calculus BC course, which is volumes. To start out, we need to establish the general form. We know that the volume of a solid of known integrable cross-section area, A of x, from x equals A to x equals B, is the integral of A from A to B. In order to find the volume using cross-sectional area, we use a method called the method of slicing. To apply this formula, you use the following steps. First, sketch the solid and a typical cross-section. Next, find the formula for A of x, the area formula. Then, find the limits of integration. Finally, integrate A of x to find the volume. Let's do an example. The region between the graph of f of x equals 2 plus x times cosine x and the x-axis over the interval -2 to 2 is revolved about the x-axis to generate a solid. Find the volume of the solid. The first step is to draw the graph of f of x. The next step is to revolve it about the x-axis, which just means to reflect the graph. Once the graph has been revolved, we can see that the shape generated is a vase-shaped solid. The cross-section of a typical point x is circular. The radius of the circle is equal to f of x. Now that step 1 of the method of slicing is completed, we can move on to step 2, finding the formula for the area of the solid. Because the cross-section is a circle, we can conclude that the formula for A of x is the formula for the area of a generic circle, pi times r squared. Using the known radius, which is the original equation f of x, and the area of a circle formula, we can conclude that the area of the revolved solid is pi times 2 plus x cosine x squared. The next step in determining the volume of a solid is finding the limits of integration. The problem states that the graph lies on the interval -2 to 2. Therefore, -2 and 2 are our limits of integration. The final step in determining the volume of a solid is to integrate A of x. With all of the information known, we can then set up the integral . We multiply by dx because that is the width of each cross-section, and we know that volume is defined as area, A of x, times height, dx. Once we have found the integral, we can use NINT or analytical methods to find the volume. The final answer of this integral is 52.43 units cubed. This same idea applies to cross-sections of different shapes, such as square or triangular, The only difference in the calculations is the generic area formula used. Another method of finding the volume of a solid is called the washer method. A washer is created when a graph is revolved and a solid with the cone-shaped cavity in its center is created. In other words, a washer is a cross-section perpendicular to the axis of revolution and is a circular region with a circular region cut from its center. The area of a washer can be found by subtracting the inner area, little r squared, from the outer area, big R squared. The generic formula for the area of a solid with washer cross-sections is pi times big R squared minus pi times little r squared. As a side note of caution to the washer method, keep in mind that the formula is pi times big R squared minus pi times little r squared, and not pi times big R minus little r quantity squared. Let's do another example. The region in the first quadrant enclosed by the y-axis and the graphs of y equals cosine x and y equals sine x is revolved about the x-axis to form a solid. Find its volume. Like the cylindrical volume problem, the first step is to draw the graphs of the two functions. The next step is to revolve the graph, both functions, about the x-axis. This creates a V-shape in between the original graph and the revolved graph. To visualize the shape of the washer, draw a circle with the top at y equals sine x to its revolved line below the x-axis. This is little r squared, the cut-out region of the solid. Repeat this step with y equals cosine x and its revolved line. This is big R, the outside of the washer. Now, to determine the area of this solid, we use pi times big R squared minus pi times little r squared. We know that our outer radius, big R, is cosine x, and we know that our inner radius, little r, is sine x. From this, we can conclude that the area of the washer is pi times cosine x squared minus sine x squared times dx. Don't forget that we are finding volume, area times width, and that dx is the width of the cross-section. The last step before setting up and solving the integral is calculating the limits of integration. The end limit of the integral is where the two functions intersect. To find this point, set the two functions equal to each other and solve for the variable analytically. In this example, we can remember from the unit circle in algebra that cosine x and sine x are equal to each other at pi over 4. This is the end limit of integration. And because we know that the graph is bound by the y-axis, we know that the beginning limit of the integral is 0. The final step in setting up and solving the integral is putting all these pieces of information together. The final integral, the volume of the solid, is the integral from 0 to pi over 4 of pi times cosine x squared minus sine x squared times dx. Now, this one is relatively simple to solve analytically. We can pull the pi out to the front of the integral, so we don't have to worry about integrating it. And we can also simplify the area equation quite simply. If you recall your double angle formulas, you can easily recognize that cosine x squared minus sine x squared is equal to cosine 2x. Therefore, the integral can be rewritten as pi times the integral from 0 to pi over 4 of cosine 2x dx. From there, you take the antiderivative of cosine 2x and get 1/2 sine 2x. From there, you solve the problem by plugging in pi over 4 into the antiderivative equation and multiplying by pi. Then repeating the process, this time plugging in 0. You subtract the answer evaluated at 0 from the answer evaluated at pi over 4, and your final answer is pi over 2. This is the volume of the solid. And that's how you find the volume of a solid using integrable cross-section area.